Yeah, so I hope I have said everything okay. Well, if not, then at least I will give you some points for entertainment. But anyway, so welcome to the very next semester, very new semester, unusual in the fact that there are some really significant changes to the schedule because, well, in theory, actually, the big building B should have been renovated as we speak, but as usual in civil engineering practice, things got a bit delayed due to some legal reasons, maybe. So we are now moving to this underground lecture room where we will spend most of our time. And by the way, congratulations on finding it in the first iteration. Yeah, it took me some time as well. Okay, so this is meant to be some kind of introductory session, so I will try to briefly introduce you what the course will be about. I will also show you some basic stuff and web page in particular, which we will be using throughout the course. And then I will slowly jump up to the first big block in this course, which concerns something which is called influence lines. So there are some people who attended the preliminary course to this one, which is called Structural Mechanics 3. So for those of you, my plan is basically to proceed along a very similar pattern. So if there is something which really you disliked in the previous semester, let me know as soon as possible. If you wrote it in that student satisfaction survey, and this is fine, I will read it tomorrow, presumably. Well, if not, just let me know via email, or just you can tell it also to me in person if you wish. All possibilities are fine. So any critique at the moment, of course, it's not really appropriate perhaps to ask that in public, but I'm just giving it a shot. On the other hand, for those of you who came from a different university and haven't seen me before, my name is Jan Zeman. I will just write you these things afterward. And again, there are some people who already have some experience with me, so you can already ask them whether this is really sensible choice and for the time, because if I'm not completely wrong, if you are Erasmus type of student, you can still change your subjects, please, no worries, in the first 2 weeks for free. Your colleagues who are officially enrolled for that course, they do not have that flexibility. People from the US and Ireland, so I do apologize for my authentic Chinese in advance. But this is the maximum I can achieve. So any suggestions? Some comments at the moment? Okay, so if not, let's proceed with that administrative and introductory part. So I put those on so some administrative stuff. So the first one is related to the course content and some really basic background information. So this is the plan for the course for this semester. Regarding the content, you can read it. If you have already gone through the similar courses at your home university, you might have a chance to understand what these individual firms mean. Well, if not, you will learn through the semester. What is important and what is really different from all previous years, I've been teaching these and similar courses, is that now actually the whole course is split into two parts. One is lecture, which is now, and then there should be exercise session, which, because of this replanning, actually, my colleagues who are in charge of that, they planned it to be for Wednesdays, which is a bit unfortunate because every month, actually the first Wednesday, I'm gone at Charles University when I serve in the Scientific Council of the Faculty of Mathematics and Physics, which perhaps I forgot to tell them. I think I did that. Obviously, the message didn't land, or I forgot. This is also possible. So as I wrote you in that email in the morning, or late morning, for me it would be most convenient to actually move the problem session from Wednesdays to Thursdays. It will not happen this week. It will start from next week and onward. So if someone has some complications because of that, you have some conflict in your schedule, please let me know as soon as possible that this is not feasible for you, because of course if there is one participant who cannot do that, then I will just stick to the Wednesday schedule and I will ask my younger and more clever colleagues to substitute me when needed.
What time would you like to change that Thursday?
Yeah, same, okay, same room, same time. Okay, then, okay, so then, yeah, the story is closed. So sorry. Yeah, so another thing is that I'm still uncertain, but there is some chance that I will go for 1 month sabbatical to France. So again, during that period, actually, some of my more advanced colleagues and younger ones will just take my role and just deliver the course instead of.
So just to clarify, it says it will be on Thursday?
Yeah. No, it will be on Wednesday. So if there is someone, and there are at least 2 cases, when you are not available, then we'll just keep it to the original schedule. And, okay, so that's it. Then there is one bit which I actually should have written to that official information, but I didn't do that. But I actually got some requests whether you can be absent from some lectures or exercises. So, well, I'm trying to do my best to record all the lectures and also problem sessions. So if you would like to skip it and listen to it afterwards, you are more than welcome. You can do it if you wish, if this is your preferred mode. A word of warning is that I'm not 100% successful in recording. So, for instance, this colleague used this past semester, and he can give you more insight whether it was worth the effort or not. But sometimes I forgot to record audio, for instance. So, in my age, you cannot ask for more. So there is no obligatory attendance. It's really up to you whether you learn it from the lectures here, recorded lectures, some YouTube videos, whatever you prefer. I mean, what counts is the result. What is, however, required from my side is that in the 7th week of the semester there will be midterm review tasks, and this is something which should be taken on site and in person. Of course, if there are some very strong reasons why you cannot participate, that's fine, you can repeat it. Some people last semester did it also online, but this semester I'm not really in favor of that. Again, unless there are some strong reasons from your side, because this, I believe, is the one which I need to offload to someone else. So I do not just want to make life overly difficult for him or her. So this is one thing which you are required to do. I'll come to that in a moment, but please note down. So some questions? Okay, so second thing is related to the grading policy. So actually there are three things for which you can get your final grade. The first one is based on homework submissions. So there will be at most 5 homework assignments, each of which is for 5 points. So you can get from your homework solutions 25% of your final evaluation. So this is one thing. The second thing is that midterm review test, which I already announced. This date is not solid though. Yeah, well, it's actually wrong. So it's 5th of November because it will be taken on Wednesday. And for this test, there is some minimum threshold to be passed, so at least 50%. It covers basics. Sorry, what is wrong then? So yeah, you know, some dates may be wrong. I may drift by from earlier or later. So if there is some inconsistency, please let me know because chances are good that. No. Yeah, if you have already attended my class, you know that you need to be very careful with what I say and be always alert. Anyway, so this should be 5th, but I will check it out after the lunch. Here really, you know, compared to the final exam, I believe this is quite easy. This is just to motivate you in the half of the semester approximately, just to review the basics and prepare you for the second part of this course, which is a bit more theoretically demanding. And then there is final exam, which will take place in January. And the overall grade is just, you know, the combination of these 3 contributions and standard grading scales. So nothing exotic, I would say. All the homework assignments and submissions will be done via Moodle. It worked quite okay in past semesters. And the only possibility is that I correct the homework solutions too late, and I'll do my best not to repeat the same mistake again. So that's it in terms of your evaluation. Another thing that I would like or love even to hear your feedback is that in the structural mechanics 3 course, actually there was something like 12, 15-ish participants. And actually I had something like 5 or 6 terms for the final exams because I was trying to be very flexible, but this is not the experience I would like to repeat in this semester. So if you can somehow, you know, agree on 3 to 4 terms in advance, for instance, it would be much appreciated from my side. Because again, my feeling is that, you know, I spent too many times preparing the assignments, correcting them, publishing the corrected solutions, etc. But this is really not a pressing issue at the moment. So any questions related to this? Is everything clear? Okay, so then one thing which I forgot, and that thing is related to some reference materials. So for the first part of the course, I'm using this as a reference book. I learned this morning that actually there is 11th edition now. They claim that this is something which has been substantially improved. I have my doubts about that, but actually your colleague a year ago discovered one error in that, so perhaps they corrected it. And as we move to more advanced topics, I will just give you some additional materials to read. The last semester I noted one criticism, which is well founded, I think, which is related to the fact that because this is US-based textbook, they are using completely different notations for internal forces. For instance, they are also working by default in different coordinate systems. I acknowledge that critique, this is fine, but I'm unfortunately not in a position to write like that by myself in my spare time because I have no spare time left. So that's it. I'll also try to make it, self-contained in terms of lectures and some supplementary materials I can do. What I also would prefer is to write everything, here by hand, such that I'm not too fast, but for the next lecture I would like to prepare some handouts and try whether this is really something better or not, because my feeling is that then I'm too slow and people fall asleep during the lecture, which is not very encouraging. And it's my feeling. So again, any other questions, remarks? Please try as soon as possible whether the access to Moodle works. If not, then let me know and I'll do my best to resolve this issue, which means that I will just forward it to someone else. Yeah, because sometimes in different courses in particular, people realize that actually they have no using that property. At the instance, they are submitting their homework. Usually there is some deadline, so you can miss the deadline because of that. So any other questions, remarks? Okay. So, yes, yes. So I sent the wrong link again. Oh. Yeah, I really do strange things. So if that happens, just let me know. I mean, it works. Okay. So perhaps you are not registered. So in the morning, I just uploaded the rest of the registered students. And again, if you face some difficulties, please let me know after the lecture. We can try it. I can have it whether you are registered for the course or not. But in previous semesters, this was the part which worked okay. The part which was not working so much okay was us accessing these annotated handouts, for instance, from OneDrive. For that purpose, I'm just using some different storage mechanism for that solution. Okay. So one thing which I will keep repeating throughout the course, I'm afraid, is that again, at a university, I really do not feel proper trying to force you to be present here in person. You are grown-ups, all of you. So if you will attend a lecture and or exercises, I really appreciate your effort. And vice versa, I would also appreciate if I do something wrong, something is not really understandable, etc. Just let me know, and we can discuss it afterward. For instance, afterwards. Sorry. Usually, your time is lost already, but at least for the next iterations, of course, I can take your suggestions into consideration and improve it hopefully next time. So this is also much appreciated. Yeah.
Will you provide extras from the book or something?
Yeah.
Okay, so we don't have to buy it from the
No, if you just write me, I will just send you bits of PDF, but the 10th edition can be found somewhere, but of course not officially. Or you can purchase the book for something like £40, I guess. But, do it your own way. Or I can give you some copies or something if you wish. But again, I do not know who that was actually, but someone mentioned last sem, this was you, right? That the book is not super helpful because it uses different notation and different terminology of it. Yeah, so for that I do it. But it, you know, the letters could mean exactly the same thing. Yeah. And unfortunately, I'm in no position to convince US universities to adopt our system, which is good for them, I think. Okay, so any other questions? Any other questions, remarks? Yes?
We're taking another course from Sam, so.
Oh, we can listen to the recording, listen if you want. Okay, so now I said that I will introduce myself, so this is now the official timing to do that. So as I already told you, my name is Jan Zeman. I'm affiliated with the Department of Mechanics. But regarding some possible on-site consultations, the situation is a bit involved. Because as I already tried to explain to you, the original plan and claim by the management was that actually we won't be able to use our offices at this very moment. So for that reason, I have relocated to the Czech Institute of Informatics Robotics and Cybernetics, which is actually this plastic building close to the metro station. So my office is actually located in a room, sorry, 223 third. So if you would like to visit me in person, just let me know in advance. I will pick you up in front of the building, and starting from that, everything will be fine. So this is one possibility how to get in touch. Another possibility how to get in touch is to have a look at my webpage, which is Open Mechanics. group/people/Jan Zeman, and in there you will find a link to my agenda. So you will just look at this agenda. You find where you have time in chunks of time in which I have those. You will just write me that you would like to meet online or offline during that very specific time slot. I will send you an invite. It will appear in this agenda, and if it is in agenda, sorry for repeating the same story again, there is solid chance that I will be waiting for you either at MS Teams or in person. Well, again, you can check it with the colleagues who attended the previous course, whether this is reality or just false promise from my side. Might not be 100% sure, but this is the best what I can offer. So if you just type that address, which I also sent you in that introductory email. So here is the link I told you about. This is my web page. This is my agenda. And you can see that, for instance, so today I'm teaching class. So this is my preferred way. If you would like to do it in other mode, and let me know. If you would like me to really announce some official office hours, I'll do it. Just ask. I don't think it's really necessary in all honesty, but again, I'm very much inclined to do so if you think this is reasonable way. Okay, so that's it as far as the organization issues are concerned. So any questions, something which needs to be clarified? Okay. So now let's briefly move to this slightly less administrative part of this first lecture, which concerns, the scope of things I would like to cover with a bit of your help, of course, in this semester. So there are three topics which I would like to cover. So this course, which is 13A STA, Structural Analysis, again, consists of three major blocks. One is something we will start already, which is called influence lines. Again, I do not know whether you have heard it before or not. Then there is the second part, which bears different names. I like to call it matrix statics. But this is matrix statics of frames and trusses. Okay. And then there is one bit which is actually related to extensions of those to some more interesting structures. And I will just proceed in two steps. So one is something which is called 2D elasticity, or load-bearing walls, if you would like to. So this is yet another chunk of material. And final bit is focused on something which is called thin plates. Okay, so that's it. So this is what I would like to cover in the course. First are these influence lines, which is something which is completely new, unless you already heard it back at your home university. This matrix statics of frames and trusses is something which is really heavily dependent on the part of the previous course, the structural mechanics 3E. So here I will assume some previous knowledge. When it comes to 2D elasticity, I will again assume, but I will recap it briefly, that you went through equivalent of the course, which at this university is called Theory of Elasticity, but it's just ordinary strength of material course. And these thin planes, again, as far as I'm concerned, this will be some new piece of information presented. So there are some prerequisites for the course, and these are mainly here and there. And throughout, I will just assume some basic familiarity with fundamentals of structural mechanics, mainly for statically determinate structures. Okay. So for these influence lines, there are three subtopics. One is related to statically determinate structures. This is something I would like to start today. Then there will be extension of statically indeterminate. And then, oh, sorry, my bad, this will be just the last topic. The intermediate topic will be then extreme load effects. And the third one will be statically indeterminate ones. This matrix statics of frames and trusses decomposes into trusses and frames. And there is no further subdivision in here. And the reason why I'm actually organizing in this particular manner, that at the very beginning we will mostly rely on hand calculations. But also, at least for this statically indeterminate, we will just also need to rely to some computer code. And there is one particular specialty at this university, which is that we have our own teaching focused tool, which was prepared by one of our PhD candidates. And it's called EduBeam. So we will do this statically intermediate analysis in EduBeam, and also somehow use some information from that in terms of matrix statics or frames and trusses. And here we will make just the final transition, which will just help us in the rest of this course. So at a certain stage, we will make a switch to something which is called MATLAB, which is an acronym of Matrix Laboratory. Which is very old and very successful code, which, as the name suggests, actually has some means how to treat matrices efficiently. In terms of writing simple, instructions, how to manipulate them, up to computational efficiency, although this won't be so much of our concern in this course. And actually, structural mechanics is one of the things where this was used in the very first instance. Because it turned out that all structural mechanics can be very conveniently written in terms of matrices. If you recall, those of you who attended the structural mechanics 3 course and passed it successfully, then I wanted to highlight one notion. That notion was stiffness matrix. This was some collections of numbers we actually extracted from the code. So it turned out that actually this is the most important stuff from the previous course, because this allows us to analyze structures on the computer. So in brief, at least as I see the course, is that this is some kind of, initial warm-up phase. This is connection to the structural mechanics 3, but actually the focus is on this part, and my motivation is to explain to you on how, in principle, the codes which you are using in more advanced analysis work. It has also some consequences in terms of, analyze, very quickly, trust the results or not, what is accurate, what is less accurate, etc. So this is something called trying to cover in the final part of the lecture. But again, I would like to make you aware that at certain point we will just switch to something which is more computationally oriented. There will be no heavy coding involved. I will just hide everything into functions which I have already prepared for you. But this is just to avoid these very tedious hand calculations. So if you still recall how that part from the previous course of the general displacement method worked, this is exactly the point in which matrices and some simple programming language can save you a significant amount of work and also significant amount of numerical errors when looking through the process. So that's pretty much it. Is there someone who has some prior experience with MATLAB, or this is something completely new to you? Okay, so at least you will learn something new during the course. Is there someone who has some prior experience with Python? Yeah, so I'm afraid that for this new the accredited studies, my colleagues decided to turn into Python. If you don't mind, I will just stay with MATLAB this semester because I have everything great. But in terms of its use, it's not so much different, I would say, from Python, because all nice things they of course stole and implemented in MATLAB. So it is. There is a version which is available to all registered students, which is fully online. You can access it using your credentials from CTU, and it has something which is called notebooks, although they call it differently. So if you have ever used this Python notebooks for some parametric studies and things like that, so I will give you exactly the same thing, but for MATLAB. So in terms of comfort of use, this is something which should be comparable. It's even a bit more comfortable because this particle language is designed for treating matrices. Okay, so that's pretty much it. So any questions? So if not, I will just move to the very first topic, which concerns something which is called influence lines, although the title is a bit less accurate, I would say. And I would just like to, give you some brief idea what this means. So what is so different about influence lines, and also what this is potentially good for. So far, actually, the standard setup was that we were analyzing some structures, which I will just show here by something very simple, like this one, for instance. We have some loads acting at a structure. And what I was interested in is what happens at the level of some cross-section. So this is what was mostly interesting for me. And depending on your preference, you have introduced some parameter to take into account that what is happening in the different places of your structure. So this X from this point onward from this point backward was primarily used just to parameterize your position within the structure for a load which is fixed. So the argument which I would like to make that what we were using so far is that this X, this cross-section location varies, whereas the load itself is fixed. Okay? In terms of its location, magnitude, etc. So these are the models we have been concerned so far. And the objects we were interested in, I will generally denoted as Q of X, where this capital Q is some quantity of interest. And the quantities of interest we have considered so far were mainly in structural mechanics related to the deflection or sag of that beam at cross-section X. So this was one thing which we were interested in. So as a result of the load, the beam somehow deforms. And yeah, well, this is utterly wrong, sorry. Or this is just a sketch. And what we are interested in is what is the vertical displacement at a given cross section. So this is just an example. So again, the other thing we were interested in, particularly for structures which are subjected to, sorry. So what we are also interested in is some of these objects which I now list here. These are called internal forces. And this N in particular stands for something which is called normal force. This is something which is called shear force. And this M is bending moment. Again, if you just have a look at this reference slide book, the letters they are using there are different, but the meaning is the same. Okay. And I would just like to remind you that in order to visualize these forces, visualize a bit strong word, just imagining what these are, the only thing you have to do is just to have a look very closely what is happening around your cross-section of the interest. Zoom in. And just have a look at the forces which are acting at this very small segment. Where I would like to remind you that if these internal forces, if positive, they are oriented in this direction when it concerns the normal forces. For the shear forces, the positive orientation is this one. And for bending moments, the positive orientation is that one. And again, I don't know how people do it at your home university, but here in Prague, or perhaps in the former Soviet Union satellites, we usually depict it in this way, meaning that this is positive orientation of the forces. And this is something which is called bottom fibers. Okay. This can equally well be represented or explained by saying, by referring to something which is more in the spirit of strength of materials or elasticity, which tells you that actually, this is the solid part of the structure which remains. from this original one. So I just separated it from the remainder of the structure by these two virtual cuts. I got new surfaces which are virtual in the sense, but these forces exactly take into account the effect of the remaining part of the structure. And I will say that this is something which is called positive surface or positive area. This is because the missing part of the structure goes in the direction of the positive x-axis. This is something which is called negative surface cross-section area, whatever, because this goes in the opposite section. And if this red arrow goes along or in the opposite to the coordinate axis, then the rest follows. For that, we also need to invoke the right-hand rule, which says that if I just orient myself along the corresponding axis, then the fingers of my right hand, they show what is the positive mean of rotation, and this is precisely here. And finally, I also need to introduce some kinematic quantities which are somehow related to those, and we will use this a lot in this course, which is called W, the vertical displacement, the deflection. If there is horizontal displacement of my cross-section, which is usually because there are some horizontal forces acting on the structure, it's called U, and the cross-section rotation is called phi. So this is what I have already explained. This is horizontal displacement of a cross-section, and this is something which is called cross-section rotation. And I hope and this x, y, z, these are coordinate axes. Yeah, so for those of you who attended the previous course 1 semester ago and have really good memory, this is something which I have presented to you also at the very beginning. Perhaps in slightly different mode, just not to have it exactly the same. The reason is that there are people with different backgrounds, actually not this time, also coming from different universities, so we just need to set some terminology on which we will align. And I also forgot that the thing we were interested in as well in this particular case were also reactions that quantities of interest. So sorry, this is something which was missing in my list. So now I threw at you a bunch of, terms, symbols, etc. So is this something which you somehow find, natural or not, or you are used to something different from your home university? So any difficulty with that? All is fine. You all know what I meant by these individual terms. Perfect. Okay, so this is the mindset we had up to this point. In the part which will be dedicated, that's the word I was searching for, to influence lines, you need to switch your mindset. The situation is different. You have the same structure. Just for the sake of argument, I will just, I'm sorry, this is something I should not have done. I will just let this concentrated force here survive. And I will also pick precisely the same cross-section. Which I will also highlight in red. Okay? The difference with the previous setup is, however, the fact that what I now allow to move is not the cross-section, but the force itself. Okay? Whereas the cross-section is the one which I picked at the very beginning, and it will stay constant through that corresponding part of the analysis. Okay? So this is now something which varies. That X. And this is something which is fixed throughout the analysis. Okay, so I pick one cross-section, and I'm interested in certain quantity of interest as it changes because of moving load which traverses through my structure. Okay, so applications are a bit obvious in this particular case. If you have car or something like that, just moving along your structure, this is exactly what you need. If you have some cranes which is carrying the weight and trying to transport it there, this is precisely what this force represents. And perhaps you can come up with better ideas. So this is it. Again, it is not, looking what is happening in all cross sections of my structure for a fixed load. This is exactly the reverse. I'm looking at one particle cross section, but I'm interested in what changes if my force moves from left to right. Okay, so I told you in the previous semester that in some stages of analysis by the displacement method, you need to change your mindset from end forces to internal forces, and unfortunately I need to repeat the story in this course as well. So this is yet another change of path, so to say. You really are computing something completely different. So I can also, formally write down this Q, this quantity of interest, and this quantity of interest is usually this thing, but can be also the displacement, but this is something that I will not show here. But it's usually some force-like quantity, so either internal force or reaction, if I'm interested in one support in particular. And I would like to know what is the value of this particular place as this force moves over my structure. And just to make it very explicit that I'm talking on something different from the left or right, because people usually mix it up, and yeah, I mix it up as well as a student, is that I will put here this eta here, but you can put any different name associated with that, and this is what tells me that this is not this quantity of interest. It is something different. It is not shear force in the given cross-section, it is something else. So did I make myself clear? Okay. So again, what is the summary of this introductory part is related to this notion of eta, or any different letter or symbol or whatever you wish, Q of X, well, this Q is this quantity of interest this X here parameterizes this position of moving load, and this eta here is to highlight that this is influence line. Not this quantity of interest. And again, this was meant mainly as an appetizer. So now we will spend some lectures and problem sessions or exercises trying to understand how these should be are constructed, starting from some basic principles up to something which is a bit more advanced. But of course, just to start the motivation properly, are potential applications. So these potential applications are at least threefold. And perhaps you can bring something new, some new viewpoint. The first one is really to analyze some extreme effects of moving load. In a very special regime, in the regime in which this car moves rather smoothly, so it is not really speeding up. Because in order to apply this analysis, I still need to live in the safe world of statics, meaning I can neglect inertia. But again, there are quite some applications of that. The second one is related to something else, and is related to the fact that you have some distributed load which is light or it is not permanent. You have your structure of interest, and you wonder how to distribute this load, which is distributed in a way that for quantity of interest, you actually achieve the least favorable situation. Okay? So I have some distributed load with which I can play. I can distribute it anywhere I want. So I would like to find out what is which is the least favorable action. And the third one, but this is something I will not cover in this course, is that you can also use this terminology to compute quantity of interest. So to get this Q for arbitrary load, because this influence line is just mechanical interpretation of a object which is known from mathematics, and it's called Green's function. Which actually is based on the observation that if for your mechanical problem you can get the response of the structure for arbitrary point load, then for any other you can just obtain the result by integrating cleverly these contributions, provided your structure is geometrically linear and also linear in terms of this mechanical performance. So I do not know whether this is offered in the English track of studies, but when I was a student enrolled in the Czech version of this program, if you decide to specialize in statics, there was some introduction on pre-stress concrete structures, and in that, just to take into account the pre-stresses, it turns out that this is actually quite a good method how to incorporate them. I'll also try to demonstrate by showing you these sequence lines from some of the books, in which people really took significant effort in computing them for various types of structures, and they tabulated them. So they didn't put this huge effort into it just for fun, but people were using it fast, quite intensely. We will just use it as a check that there are calculations. So that's pretty much it. I just need to check what I'm supposed to do. No, I still have plenty of time. Sorry. So now let's try to have a look how this works. And we will just start by simple examples. And what I would also like to use this opportunity for is just to refresh a bit your memories or knowledge of how to determine the internal forces and things like that. So how this works by direct calculation. So I will start with the first example, which will be really simple. So this will be statically determinate structure, in particular cantilever beam. So I'll try to be a bit more cautious now. So this is this graphical representation or a model of my structure. And just to rely a bit on your help, what do you think the thick horizontal line signifies? So what is the information I would like to show by drawing this thick line? Geometry. Kind of, yeah, partly. But, you know, this is something like this one, so it also has some perception geometric characteristics. So this is what this line cannot give me. So how this is called? Sorry? No. Center line. Center line. Yeah, this is the word. Yeah, it is center line. I do agree. But the word which I was begging for was center line. Because I'm using basically 1D model for my three-dimensional object, I'm just representing it by its center line. By side. Okay. What do you think this graphical symbol stands for? And really there can be some disparity here because in other countries people just may decide to use different graphic symbols. So what do you think this stands for? Yeah. So it's called with different names, so it's called fixed support. It is something which is built or built in or clamped, you know, and as I did not appreciate the last semester, if you are a native speaker, you probably know a bunch of additional adjectives instead of these three dots. People call it differently. Okay. What this means in particular. So if I just write it, if I just draw this scheme, what is the information I'll try to store in the picture? Sorry? Yeah, 3 degrees of freedom are out. Nice. Out or fixed or whatever you like to call that. But now there is a question what you mean by the degree of freedom and why 3 and which 3, right? So what is, in your opinion, the degree of freedom? Perfect. Yeah. Excellent. So you know, this is a bit elongated version of that. This is the center line. Now I just need to keep track of this left and what is wrong, which is most difficult for me. So what this scheme says is some information about this cross-section in here, right? And it says exactly as your colleague suggested that this cross-section cannot move horizontally, cannot move vertically, and cannot rotate. right? So this cross section, this one, okay? And I do agree on that. So now using these bunch of letters and symbols which I threw at you, how I can write it down in a way that I'm recycling them. So where in this scheme I have something which tells me about the horizontal displacement of cross section. Yeah, so it cannot be in top because I'm too short to reach there. So it must be in bottom. So it's written here and it carries the letter of U. This is this W, and this cross-section rotation is something which I denoted as phi. So in fact, these are the 3 degrees of freedom, and the statement that they are out actually means that the U, sorry, and if you are making your own notes, please leave some space here. Yeah, but more clever than myself. So after the letters. So these are the 3 degrees of freedom which are taken out. They speak about this cross-section in here, which is even not shown here, but it exists. And we are just, at least at this university.
Omlouvám se, že ruším, protože vlastně přijde můj kolega, kde všechno funguje, jako.
Akorát to není jako normální table, musíte promítat. Nebo psát do table.
Jako být svůj zdroj, jako jo. Tady počítač není.
Ne, počítač tady je, tady, ale nemůžete psát jako na tabli,
Jo.
ale můžete psát do tabletu nebo promítat.
Okay.
Now I got a bit lost in the argument. So what was the argument I was trying to make? Can someone steer me in the right direction? Alright, something needs to go after the letters. Yeah. Yeah, so it was some nonsense previously, which I forgot. Okay, so you know these are zeros, which are nice, nice numbers. But these are some physical objects, so they also, or some physical, not in reality, although they can be measured actually. But it's something that comes from physics, and things in physics usually come with units. So what is the unit of that U, W, and phi? So this is the horizontal displacement. So if this is displacement, then it is measured in meters, perfect. Same for vertical displacement and cross-section rotation. Yeah, by degrees, or I like radians, but it's equivalent, but it's dimensionless. This is the most important thing. Perfect. Okay. And finally, you know, I put this parentheses in there and wrote that there is some function of x in the place. So in order to be able to speak about that, I need to introduce my coordinate system, which is done in the standard way. And that standard way in the Czech Republic and all similar countries is actually related to that as in normal world, that x, coordinate axis runs from left to right horizontally, but actually the perpendicular one is not called y, and it's not pointing upwards, but it's called z, and it's pointing downwards. Now this is something we even have some sort of practice of that, which is called coordinate systems in structural engineering or something like that. And this is really what is used here by default. If you don't believe, then ask your colleagues, then I'm not inventing it. So this is some Czech specialty, so to say. So can someone confirm that Is there someone from university in which by default in 2D the vertical displacement is actually not downwards but it's upwards? So I'm almost certain that there should be one person from the US, so in that they do it differently. For Ireland, I don't know. In Portugal, some people told me that they're actually using this. So this is the coordinate system I will be using. And in order to be able to write something in there, I also need to specify something. And that something is what is the length of this cantilever. And because I do not like numbers in particular, I will just write here the capital L if you wish, but you can just write out a meter if this is something which you find disturbing. Okay? So if I say that all quantities of interest, and these are possible quantities of interest, are parameterized by x, so if x equals to 0, I'm here, and vice versa. So what I should put in the formula, well, that text here. So what should be put in here, and in here? So x is something which is called variable, which is because it varies. It can be something, everything from 0 to L, if I would like just to consider that reasonable scenarios. So what is the letter which I need to write there? L, precisely this one, because this stands for the length of the beam, and this is something which is constant. So what I say in particular is that I will take this u as a function of x, but I'm not considering arbitrary x, I'm considering complete. But I'm too lazy to write it in this fully blown up version. Again, you know all that stuff with high probability, just to make sure that we do not lose each other at the very first lecture. That would be a bit embarrassing. Okay? So this is the standard setup we are used to, but in the framework of influence lines, actually the situation is a bit different, because this x now, it signifies something different. It tells us where this movable force of intensity 1 is. In some German textbooks, they even, plot it differently by this wiggly line. I won't do that, but this is just to say that this is my force, and I will explicitly write here the dependence on x. So this, as a function of x, means that I will take my force of intensity F, I will position it here to the coordinate system and let it travel in the direction of the positive x-axis by the parameter or variable which I choose. So this is one thing. And the second thing is that I need to pick my quantity of interest. And that quantity of interest is attached to a certain cross-section of interest, and that cross-section of interest will be this one in the middle, right? Or somewhere else if you wish. It is not associated with this variable x. It is associated with half of L, that half of L is constant and doesn't change during the analysis, so this is fixed. And the usual way how to highlight that is to say that I have some cross-section A, some cross-section B, so I'm adding one additional cross-section just for the sake of analysis, which is called C, okay? And now, let's have a look how two quantities of interest look like. The first would be VC, meaning the shear force in cross-section C. And the second one would be the bending moment in the cross-section C. Again, you can write it differently if you wish, but what I would like to highlight is that this is not an argument of ABC, this is just specification of that particular cross-section. So I would just like to perhaps highlight it by this. Unlike the classical analysis, this is not a single value, this is function of x, which again usually is not explicitly written down, but in the first one, I'll just do it. And just to highlight that this is not one value of the internal force for that load I just plotted there, but it's something different. It is a so-called influence line. I will put in front of that this eta. But again, you can pick any other way how to emphasize that, right? And in order to plot those, actually, we just need to play that standard game. And that standard game consists of taking my structure of interest, which is again represented by this center line, looking at the at the cross-section of interest, which is right in the middle here. And now again, the particle technique can vary. But again, for the sake of argument and make the argument as easy as possible. Sorry, this is not what I wanted to say. What I wanted to say that now, my structure actually splits in two parts. This is not in reality. This is, of course, my mental experiment, or I don't know how we would like to call it. So for a moment, I would imagine, I will imagine what would happen if the structure was split in two. So this is here and this one is there. These are the center lines again. So black and thick. And I know that in the previous semester I advocated it with some way of analysis of the internal forces, but only after that I realized that actually in this very course, that standard way how people do it, they would like to introduce it for the first time, makes more sense in this particular context. And this is related to the fact that now I will imagine my internal forces as they act there in the cross-section C. If I just refer to this particular scheme, then this is the orientation of the forces I should take into account on the left part of my structure, because here there is this cross-section to the left, there is the structure, to the right there is nothing, which is precisely what happens at this cross-section. So I would just like to highlight it a bit. And the orientation of the internal forces would be aligned with the orientation of coordinate axis. And here I would have this shear force, normal force, and bending moment, all of them in C, cross-section C. And by the courtesy of Mr. Newton, I actually happen to know that because these are two bodies in contact, I just enlarged this gap only virtually. On the opposite side, I need to have these three forces acting like this one. And these are the same ones in magnitude, and they have just the opposite orientation. Here I will also have reactions, which I do not know and do not want to compute because I'm a very lazy person. And on this structure, I have the force, but the force which moves, right? So I will not draw it in that more elaborate way, but I have the force which moves of intensity F, just to make the argument. So in fact, I can encounter two scenarios. One scenario is that this parameter x happens to fall between 0 and L half, which means that the force will be located at the left part of the structure. And what happens if the force actually moves to this part? Yeah, if you are so much obsessed with details as I am, then please know that here these all inequalities are not sharp, meaning that I'm not saying what is happening exactly at the beginning and in the middle of the structure, because I know from my previous experience with structural mechanics that internal forces, they like to jump and etc. So I would be a bit more cautious about that. Well, if you do not know what I'm talking about, then just forget that. So again, I have two scenarios. In one scenario, I have the force located on the left part of my structure. So I have here this force F. And on the right side of, and of course then the situation when the force F moves to the right part of the structure, but this is a bit, difficult to draw on this expanded thing, so I would just like to visualize it using this picture, but perhaps there is a better way. But this X can vary, so it is a parameter of variables. Okay, so here I have two situations, and again I do apologize to all of you for which this will create some complications. But the argument which I now would like to make is that internal forces ensure equilibrium of each part of the structure. Which means that I need to write equilibrium equation for well-chosen part of the structure. And if you think it over and would like to do spend your minimum effort in that, this right part is prohibited because there are reactions acting here because I constrain it in this particle manner, as you nicely explained to me. So I will always base it on the left part. So I will just write down the equilibrium equations for the left part. And in this case, actually, that these variables become x-dependent. So there are no longer conventional internal forces, but are influence lines of those. And if you just have a look at what I wrote in that problem part, I was nice to myself and I said that I do not want to know what is this normal force because it is identically equal to 0 and hence it is not really interest. So just to proceed in the standard order, meaning starting with something which is easy to something which is a bit more difficult. So now I can forget about the right part in here. Sometimes I try to delete that part, but then I forget always to return it back, so I will do that. So if I just have a look at this left part in here, so there is no force. If my force F moves past that cross-section of interest, it does not cause any external forces at the left part hence here. Or if you would like to put it differently, actually this constraint here, this support takes all effects of the forces, so it does not need any help from the internal forces on top of that. But independent of the argument which you make, it actually turns out that this influence line of shear force at cross-section C for these values of x, which again signify the position of my force of interest, they are identically equal to 0. Okay. So once the force passes the cross-section of interest, there is no effect at all. Okay? I told you before that because unfortunately or fortunately we are not in the world of mathematics but in applied physics in certain sense. All numbers have some units. So what is the unit of shear force? Yeah, newtons. Yeah. Bending moment has the units of Newton meters. Okay. Now the first situation where x lies before 0 and L half, will be a bit. It will be also easy, but I would just, for the sake of the argument, I would like to analyze it separately, because this is for the very first time I'm showing this. But I will hopefully never ever do it again. So now in my interpretation, actually the internal forces which are now which come with more fancy notation now, try to make sure that this piece is in equilibrium, which is actually the reflection of the fact that the structure as a rigid body does not want to move anywhere as a rigid body. So in order to make sure that this doesn't happen, I need to ensure that the structure does not move vertically, this part. So I need to make sure that the vertical resultant of the all forces equals to 0. And I also need to make sure that around arbitrary point, actually that force does not contribute to. The resultant movement, I think, at the structure equals to 0. Sorry. Stupid argument. I can also could have written that horizontal equilibrium equation, but there are no forces pushing it horizontally, so this is something which is satisfied automatically, and I do not need to bother about that. And now, if I just write down the vertical equilibrium equation, what I will get is that this internal force now, with some additional symbols, plus the force which is moving at the structure equals to 0. You know, now this equiflex I'm not using anymore. And so the only thing to ensure that as a rigid body the structure do not want to move, what I got is this one. So this equation. And as for the bending moment, I will just write the bending moment equation around the cross section C to find out that I have this contribution of the unknown moment which rotates in the same direction as this one, plus, and now I need to compute the moment of force with respect to this axis or point. So this is the force F, and I need to multiply the arm twice to rotate this axis or around that point, depending on what my colleagues previously taught you here or at your university. But here I have to be a bit more careful, because I know that from this cross-section to the cross-section of interest, I have L over 2 meters. From the free cross-section to the force, I have X. So here I have this L over 2 minus X in here. Okay. So now I will take force times arm on which this is acting. This is assumed to be positive because X is between 0 and L2. This is also positive. So overall, I reflect in the equation the fact that this force is trying to rotate with that axis or point in the indicated direction, and this adds up to 0. From which I immediately get that my influence line of bending moment at cross-section C as the force moves, as indicated, is this value but with the minus sign. So this is F times X minus L over 2. So I got what I promised. I got some functions of the variable X. These functions are pretty easy to express because their dependence is actually visible only in here, on this one interval, and just for the influence line of bending moment. And yeah, and these are zeros. So if I just use the rules which we incrementally introduced in all previous courses on how to draw diagrams of internal forces, I'm getting my influence line of the cross-section, shear force in cross-section C. As the following picture. So sorry, this will be a bit less organized. So if I just imagine that, this is my cross-section C. So if you recall, I had the constant value of minus F in here, and the value here is identically equal to 0. And the magnitude is F. Whereas for the influence line of bending moment I see in the precisely same cross-section, I can copy the value 0 here and this VR0 is just normal zero. I do not know even why we're writing that. In between, I have this linear dependence on x, which I usually denote here by saying that this is first order polynomial. And I know that first order polynomial is uniquely defined by two values at any points of interest or cross-sections of interest. So in particular, mine would be at the beginning and at the end. So if I say that my x equals to 0, this formula tells me immediately that the value of the bending moment is f times L over 2 with the minus sign. Here I will follow what is again used in this country a lot, which is related to the fact that if the bending moment is positive, I will just draw it downward in the direction of the z-axis. If this is negative, I'm just drawing it on the opposite side. Well, in this course, I'm aware that you can use just different conventions, but just be aware, for instance, in more practically oriented courses on steel structures, etc., that some people really require it here. Perhaps no longer, but when I was a student, they were really picky about that. And if I would like to compute a second value, then I just say that this is L over 2, the second point of the definition domain, and actually this term then identically vanishes, and this is how it looks like. So the way I would like to plot it is this one, but any equivalent expression is fine with me. I'm just plotting the graphs of these functions, which are really easy to plot because there are the most complicated dependence is linear. Okay? And now you can play this game by in multiple scenarios, meaning that you can pick different cross sections, you can pick different quantities of interest, but the story is still the same. Okay? So this is what I wanted to show by this example. I'm already 3 minutes over my limit, and there are some people who are very interested in telling you some additional stuff. So I would like to stop it here. I'm really looking forward to meeting you on Wednesday, in which we will postpone this for a moment, but I will do some recap on how to solve some more complicated problems and check them via FGD. So again, if you feel that this is something you know very well, well, you can invest your time in some different activity, but I would be delighted to see that here in person. Okay, thank you very much, and see you on Wednesday. So the recorded lecture